So here's just a quick primer or review on Newton's method. And this particular method is designed to help us find the zeros of a particular function. So we can see here that we have some smooth and continuously differentiable function, f of x. And we can tell that at least on this interval that we have displayed here that there is one intercept. And the question is, how can we find that intercept? And more importantly, how can we use a computer to find that intercept? Because we don't know what f of x looks like, and it could be a much more complicated function. But the first thing that we'll want to do is we'll want to kind of give the computer some bounds to figure out where we want to look, right? So we might say, hey, computer, I want you to take a look from A to B. I'm reasonably confident that there's a zero in there. And so the first thing that we'll need to do is we'll need to take a look at f of A, and we'll need to take a look at f of b, and we need to make sure that the sign of f of a and f of b are opposite, right? Because if they're both positive, well, that means they're both above the x-axis, or they're both below the x-axis. And in a case like that, you could still have a zero, right? So you could have something like that, where your a is here and your b is here. So you could have zeros in between them, but typically we want to be more confident than that. So we really want to know that there's a zero there so that we can get after it and we can go find it. So the first thing that you might want to do is just say, look, f of a needs to be less than 0 and f of b needs to be greater than 0, or f of b needs to be less than 0 and f of a needs to be greater than 0. And that way we can just be sure that there's at least one intercept on the coordinates that we're interested in here. Okay, so that's where we're at there. And the next step then is, okay, how do we actually accomplish that? And what's nice is that Newton left us this awesome method, which he was nice enough to name after himself. So the first thing that we'll do is that we need to set a guess, right? So I need to just guess somewhere, and for no particular reason, I'm just going to guess right here. So let's say this is our guess. And so what information do we know immediately about that guess? Well, the first thing we know is we know that this point here is actually f of x naught, if we're calling that x naught, right? And so then if we, if we don't want to just evaluate this function f of x everywhere, what we could do is we could approximate this function. And so we could take the derivative at, f of x naught. And so that might look something like this, right? Where we have a derivative there. And we know that when we take the derivative of the function at that point, that we end up just getting the slope at that point. So this would be like f prime of x. And this is interesting because what we could do then is we can approximate the zero by taking the derivative here and figuring out what that x-intercept is. And it turns out if it's not that good, we'll just do it again. So we'll see that second step here in a second. But first, let's figure out what this approximated zero for the function is, and then we'll go from there. And so really what we're trying to do is, we're trying to say, okay, f prime of x naught, we know that that is a derivative, so it's something that we can write down. And we know that that's of the form y minus y0 over x minus x0, right? It's just the slope, right? The f prime at x0 is just the slope at that point. And of course, we know that we can write y0 as just the function evaluated at x0 over x minus x0. So we can write something like that. So let's go ahead and solve this for y, right? So if I multiply x minus x0 over to the other side, and I put the y on the left side, I end up getting y equals f prime of x0 times x minus x0. Let's see, do we get plus? Yes, we get a plus f of x0. And so that's kind of your, a more traditional equation for a line here. And obviously this is the slope here, f prime of x0. That makes total sense. But the point that we're looking for down here is where y equals 0. So what we actually want is we want this equation when y equals 0. Right, well, that's super easy. So 0 is f prime x times x minus x naught plus f evaluated x naught. And then what we'd like to do is we'd like to solve for this equation in terms of x, because that's actually what we're looking for. I want to know what this value of x is, right? So if I subtract this onto the other side and then divide by f prime of x. Hopefully I'm not doing too many steps here. We should get something that looks like this. And then I would have this equal to x minus x naught. So we'll just move x naught over here equal to x. And so x is just x naught minus the function evaluated at x naught divided by the derivative value evaluated at x naught. And so this right here is kind of what we need. Now, I've called this original guess x0, and this is supposed to be an approximation for where the zero of the function is. And instead what I'm going to call this, I'm going to call this x1, okay? So I'm going to say this is x1. And that's important because what I'd like to do now is I'd like to go back to the top and I'd like to do this whole thing again. So here's my x1, and basically what I'm going to say is, okay, this x1 that I just found, let's just start over. Let's just call that x0. And so if we trace this down and we get this point right here, and we draw the slope here, right? We draw that tangent line, we get another point, and we could just keep going, right? And we could continually call this like x1, and this could be x2 and 3 and so on and so forth. But instead, well, we want to think about this programmatically, right? Where I'd like to make a loop. And so what I'm going to do is I'm just going to reassign x1 to x0, and I'm just going to start over again. And that way I can just kind of keep applying this loop over and over again. And so let's go ahead and write out the pseudocode. Pseudocode is just a fancy word for saying this isn't program language specific. But the first thing that we might want to do is like set our bounds, right? So I might want to give, you know, an interval a and b, right? So I might want to assign a and b to tell the computer where I want it to look. You don't have to do this, but if you have some bounds, it would be nice to then maybe check those bounds. So first I want to store a and b, and then I would want to, here, let's write this. We'll go store a and b, and then I might want to check bounds, right? Again, looking for one being positive and the other being negative, and that way we know that there's an intercept in there. And then what we'd like to do is, you know, we'd like to go about establishing our initial conditions. And so the first thing that we're going to need to do is we're going to establish some initial condition x naught, right? And so I'm going to just tell it, hey, I want you to look at x equals 1 or x equals 2. I got to start somewhere. We're going to start at x naught. And then we probably also should define our functions, right? So f, I need to define what f of x is, right? And I need to define f prime of x. So just as an example, I might have f of x equals sine of x. And then, of course, we know the derivative is just cosine of x. So that might be something that we need to do, because of course we're going to need to evaluate those things. And so that's another point that I need, right? I need, you know, if we're looking at the knowns here, I've got x naught there, but then I also need the function evaluated x naught, and then I also need the derivative of that function evaluated x naught. You know, so we might call it something like f0 of x naught, right? I need to store that, or rather maybe something like this. We'll call it f0 is f of x naught, and then I also need to store f prime 0 as my initial function evaluation and my initial derivative evaluation at f prime of x0. And that's nothing more than plugging this value into that function, or this value into that function, or approximating it somehow. So then we have all of our initial conditions set up, and at this point we need to actually like loop through this process here, right? And so there's a couple different ways you could do a for loop. You know, I could say for 1 through like n, you know, some number of iterations. I could also do a while loop, you know, while I'm less than some tolerance. So whichever way you like to do it, doesn't really matter. For this example, we'll go ahead and we'll go through with the for loop. And so the first thing that we need to do is just define x1, right? Which is just x naught minus our first evaluation of the function at x0 and our prime derivative evaluation. And it's that simple. So there is our x1. Now there's a few things that you might want to do here. The first thing you might want to do is you might want to like check a tolerance. So you might say, hey, look, if that x1 is super close to that x0, i.e. these two values here and here are very close to each other, well then I might be on the 0, right? So I might want to check the tolerance. Maybe it's something less than 1e negative 8, something like that. Another thing that you might be able to do is check how many iterations you're on, right? So let's say that this loop has been running for a while and this n is quite large, right? And so I might want to keep that n lower than, say, maybe 10,000 iterations, right? If I've run that many iterations, I'm probably not going to find the 0 at this point. Either I've done something wrong or maybe I don't have a 0 here. And so that might be a nice additional check that you can put in here. But no matter what you do, whether you decide to do these or not, now that we have this x1, what we'd like to do is we just want to start back over through the loop. And so just like earlier when I said, hey, I'm just going to, instead of going x1 and x2 and so on and so forth, I'm just going to reassign this as x0, right? So I'm just going to say, okay, my new x0 is now x1, what we just came up with, right? And my new f0 is just f at x0, and my new f prime 0 is just f prime at x0, right? So we've just reset, these new values, right, back to the initial condition. So now when I jump back up to the top of this loop here, we can just run through and find the next value, all right? And then of course we can just end our function there. And so that would be just kind of a basic outline of how you might want to code this thing up in any particular language. And go ahead and try it out. Try some simple examples. Highly recommend that anytime that you write code, to write something that you definitely know the answer to, right? So you could do something as simple as sine x and cosine x. Maybe pick something near pi, and that way you should find a 0 at x equals pi. Or maybe you can pick something near 0. All right, and that is either a primer or a review for Newton's method.